So welcome back. In this video, we'll pretty much wrap it all up and see how we can combine what we've learned so far to solve systems of differential equations. So this is pretty much the last part of the chapter. We're going to summarize that. So this is 11.6. A summary of solving differential equation systems. So just as a brief recap, we are given a differential equation system of the form y prime of t equals a times y of t, where A is an n by n matrix and y of t is a vector of the form y1 of t to yn of t. So n separate functions here. How do we go about in solving this system? First question we need to ask is the matrix A diagonalizable? So can we decouple the systems? Can A be diagonalized? And the idea here is to decouple the DE system. If so, then we find an eigenvector basis of A. Find a basis of R to the n consisting of eigenvectors of A. And also the corresponding transformation matrix D. Oh, S, sorry. Let's call this matrix S. Step 2. If we have the transformation matrix S, then of course we can determine the corresponding diagonal matrix. So determine D as S to the minus 1 AS. And use the substitution. We've seen that one already. Substitution is y of t equals s times set of t. We use that to transform the original system of differential equations into a decoupled form. So to transform the system y prime of t equals a times y of t into the decoupled system z prime of t equals d times set of t. We've seen how this works. Step 3, once we have that new system, of course we can solve that. We know how to solve a decoupled system. Solve the decoupled system. Z prime of t equals d set of t. And then we transform that back. So we compute the solution y of t using that substitution. So multiplying the solution for set, what we got, by s, we get the set of solutions to the original system Y to get the solution to the original system. Okay, possibly we are going to use initial values to compute any constants that might appear in the process. So use initial values to determine constants. And of course, it might be that we have complex eigenvalues, complex eigenvectors. So in this case, we're going to use Euler's formula to deal with those. Use Euler's formula. You remember that is e to the it equals cosine of t plus I sine of t if necessary. Okay, basically that's the process. Of course, there's a lot of things that can go wrong here that we're not prepared for. And the first thing that can go wrong is, what if A cannot be diagonalized? For steps 2 and 3, we do rely on a decoupled system, on a diagonalized A. Now, 2 questions. So first question. What if A cannot be diagonalized? Yeah, of course, then our process breaks down completely. In fact, we can still do something in that case. Even if we cannot get diagonal form, we can get something that is close to diagonal form. And this is called the Jordan normal form. As a generalization, and I'll just say this is something close to diagonal form. But not quite diagonal. So it decouples the system somewhat, but not completely. And of course, that makes things a lot more complicated. That theory is beyond the scope of this lecture, so we're not going to go deeper into that. But just in case you encounter a system of differential equations at some point where this decoupling approach doesn't work, there is a way out. Just search for Jordan normal form. And of course, the second question that we did not deal with and are not going to deal with is, what about if we don't have a homogeneous differential equation system? So what about an inhomogeneous DE system? We had a brief glimpse at inhomogeneous systems in the introductory section here. We did not deal with inhomogeneous in the differential equation systems part here. Again, because that makes things a lot more complicated. So if something like that happens, it's best to not try to do this yourself. It's best to call a trusted mathematician to see what can be done about this situation. Okay? So don't do this yourself. Okay, again, this is way beyond the scope of this lecture, so I'm not going to deal with not diagonalizable matrices. I'm not going to deal with inhomogeneities in differential equation systems. And I'm also not going to deal with other generalizations. For example, the matrix A, we only consider the case of constant coefficients. Of course, the more interesting cases would be the ones where the coefficients are not constant, but depend on t, for example. Again, a lot more complications, lots of interesting theory though, but nothing that we should deal with in this course, I'd say. So this kind of closes the chapter on differential equations and differential equation systems. There'll be one more video on this, giving you an example, and then we'll skip to a completely new topic.